So we're going to take a look at this problem. At the instant shown, ball B is rolling along the slot in the disk with a velocity of 600 millimeters per second, an acceleration of 150 millimeters per second squared, both relative to the disk and directed away from O. If at the same instant the disk has an angular velocity and angular acceleration as shown, determine the velocity acceleration of the ball at that instant. So when we're doing this problem, keep these equations in mind for relative motion using rotating axes. Keep in mind this velocity equation and this acceleration equation. And what's most important to remember is there's going to be a velocity of the main body and or an angular velocity and acceleration of the main body. So in our case here, if we look back up at this picture, you can see this disk is kind of the main body. It's the one that's rotating, and that's the one that's going to have like the main body acceleration, main body velocity, main body angular acceleration. So this is the main body, what they sometimes call the rotating axis. And so I just copied this onto my paper here, angular velocity and angular acceleration like this. And I show the point B. Now the center, they call the center O. I'm going to call it A only because I have the equations already with A and B. So I don't want to change those. You could just change the A's to O if you wanted to, but I'm going to make it a little bit simpler. I'm going to change that center point to A. So I just copied this. And so what we want to do is figure out what's happening with the main body, what they sometimes call the rotating axis or the motion of the moving reference. Let's set that out. Motion of moving reference. And when you look at what we have here, the angular velocity of the main body is going to be the capital omega, and the angular acceleration of the main body is the capital omega dot. So in this case, we're going to have capital omega is 6 radians per second. And remember, it's spinning about the z-axis, so that's going to be 6k. I guess I'm calling counterclockwise positive. And then for the angular acceleration of the main body, once again, that's the capital omega dot. That's going to be 3k. Now, this is not translating. In other words, this main body is not moving horizontally or vertically or anything like that. It's just spinning about the z-axis. Now, again, we need the velocity of the center point. Now, once again, I called that A, but it's not translating. In other words, it has no linear velocity in the x or y direction or in the z direction. So the velocity of A is 0 and the acceleration of A is 0. And that's because we only have rotation in this problem of the main body. The main body only has rotation. So we don't have, those are both going to be 0. And then the next thing we want to look at is what do we have that's moving on this body? So let's take a look at that for a minute. what's actually moving on the main body. And if you look at the picture here, it's just that ball. And and uh, so that's going to be like our moving object that's on our main body. And so that's going to be our other column. And so we'll call this motion of point B with respect to the moving reference. And then that's what these values over here are, that V, B of A, B with respect to A, and A, B with respect to A, etc. So you see the ball is moving 600 millimeters per second away from the center and accelerating 150 millimeters per second away from the center. So we're going to use those for our VBA and ABA. So let's take a look at that. So our VBA. And again, they have this subscript XYZ. It'd be good to put that on. And that's going to be 600 millimeters. So that's going to be 0.6 meters per second. And then ABA, XYZ is 0.15 meters per second squared. I like that. And we pretty much have everything done that we need. We're probably going to eventually need that RBA. And so we might as well take care of that right now. So RBA is going to be the radius or the distance B relative to A. And so it's going to be 0.4 meters, because that's where B is at the time, if you remember from our picture here. At the time we're interested in, the ball is 0.4 meters from the center. So, and now, so what would that be in this case? Remember, that's going to be what it's going to take to go from B to A. Excuse me, from A to B. Remember, if it's written B with respect to A, that means you want to see what it takes to get from A to B. And that's going to be 0.4 meters. And it's all in the X direction. If you look back at the picture, it's all along the X axis. So we really have everything that we need now. And so now it's just a matter of calculating the things that we need for the equations. So again, it's important to keep the equations in front of you. And let's see what we're going to need from these. We're going to need this omega RBA and to get the velocity. So let's do that. And remember, that's going to be I, J, K. And we just found the RBA, which was 0.4 I. And we had also found omega, which is 6K. So it's 006. And this is 0.400, like this. And if you go through the steps of the cross product, you get 2.4J. And so we actually have all the information to put into our equation. Let me write the equation down. Again, it's this equation right here. And now just plug everything in. We said that VA was 0. And we just calculated this 2.4J. And then the BA 0.6 I. And so the answer then is going to be 0.6. And it'll be 0.6 I plus 2.4J. So the velocity of B is 0.6 I plus 2.4J. Next, we're going to calculate the acceleration of B, and we'll take a look and see what we need. We're going to need omega dot cross RBA. Let's calculate that. That's going to be IJK 003. That was our omega dot was 3K, and RBA, of course, was 0.4 I. And if we calculate that, we get 1.2J. And then we're also going to need this cross product of a cross product. Now, we also already calculated this. We calculated the velocity, so we can just do the cross product of that. Remember, we calculated this cross product here. We got this. Now we want to do it again on that. So in other words, we want to do omega cross RBA. And that'll be I, J, K. And once again, we're going to do omega with 6K. That's going to be 006. And the RBA, excuse me, the omega cross RBA is 2.4J. And this will be 14.4 I. Finally, we're going to need this quantity here, omega cross VBA, again, omega was 0.06K, and VBA was 0.6I. And that's going to be 3.6J, like that. And the one other thing that we're going to need is, so we got that, is the acceleration of B with respect to A, but we already have that. We know that that is our 15I. So we have everything we need to plug into this equation here. Let me write that equation down just so we have it in front of us.
Yeah. Yeah.
It's actually a pretty long equation, but we've actually calculated everything already. So all we have to do is substitute stuff. And actually, this quantity here is what we calculated here. I just left off the X, Y, Z. And then plus acceleration A, B, A, X, Y, Z. And so AB, this is going to be 0. And this quantity right here was 1.2J. This here was negative, this right here was negative 14.4I. And over here, this was plus 2 times 3.6J. And this was 0.15I, like this. And so put this into to just add everything up. So we're going to have AB. And we put these together. That's going to be negative 14.25I. And put the J's together. That's going to be 8.4J, like that. Next, we'll take a look at this problem. A ride in an amusement park consists of a rotating arm AB having a constant acceleration of 2 radians per second about point A, and a car mounted at the end of the arm which has a constant angular velocity of negative 0.5 k radians per second, measured relative to the arm. At the instant shown, determine the velocity and acceleration of the passenger at C. So again, we want to figure out, okay, what's the main body? And you can see that big arm is kind of the main body. That's the, which is sometimes called the moving reference. And that's going to be what a lot of our main calculations, our main figures will go with the moving reference. And so let's take a look at this problem. So in this case here, again, we have this big arm like this. And now we're told that, again, the radius of this round circle here is 2 feet. And this, they call this omega prime. And this is going to be 0.5 radians per second, like this. And now we're eventually going to need the velocity of this point relative to the whole thing. So let's go ahead and do that now. So you'll see in a minute why we need this. So this velocity of the point C is going to be VC. Again, of course, that's always going to be the omega R, which is going to be 0.5 radians per second. Again, this is going to be the relative velocity. Really, I can call this VCA with respect to A times 2 feet. So that's just going to be 1 foot per second. Again, we're kind of thinking, okay, what's this velocity? You know, we're ignoring the fact that this whole main axis here is rotating. We're just thinking, okay, what's the velocity of this relative to that whole thing? And that's what this is. Then we're also going to have the acceleration. Now, notice there's no acceleration here, no angular acceleration. So the only linear acceleration we're going to have is the normal acceleration. So our A normal, now in this case, this is going to eventually be our A CA, if you will. That's going to, remember, that's the velocity squared divided by rho. In this case, it's going to be 1 foot squared divided by our radius here is 2 feet. And so it's going to be 1/2 feet per second squared. So again, we're just calculating, you know, what's happening locally here. Now let's put everything together. Again, we want the motion of the moving reference. It's good to sort of organize this. And again, that's this whole system here. What's happening in the main system? You can see it has an angular velocity of 2 radians per second. And it gets spinning about the z-axis. Now, there's no angular acceleration of this whole body. So that's going to be 0. Now, the center point of this whole axis, like this whole system, is the whole system itself, the whole main body is not moving vertically, horizontally, or anything like that. So that means the acceleration of A is going to be 0, and the velocity of A is going to be 0. So that's the main system we were looking at here. What's happening with that? Now, the motion of C relative to the moving, or with respect to the moving reference. And we've actually calculated these values up here, VC, and just using the notation or equation. You don't have to necessarily put all these X, Y, Z in, just as long as you keep track of what it is. So now we ended up with this velocity. And remember, this was going this way. So that looks like that's going to be in the negative 1I, because it's going in the negative X direction. And then the ACA XYZ. Now, in this case here, the normal, that's going to be going, remember, the normal is always toward the center of the object about which it's rotating. And so it's going to be in this direction. So that's going to look like that's going to be in the positive Y direction. So that's going to be 0.5 J, like that. Now, as we did before, we're eventually going to need this radius of C with respect to A, because that's C is the point we're interested in, and A is the center of the main body that's rotating. So we're going to eventually need that. So let's take a look at that. This time it's going to be a little bit more complicated, though not real difficult. Let's just take a look at our picture again. Notice on our picture, we're at an angle of 30 degrees. And so let's maybe sketch that. So we have 30-degree angle. And we have this thing, that smaller circle rotating about B. And let's sort of write that down. So we have this, and we know that this is 10 feet. And so over here, now again, we're interested in the point C, but we're going to have to do some other stuff here. So again, this side here is going to be 10 cos 30 degrees, or 8.66 feet, like this. And then this side over here, this whole side, that's going to be what, 10 sine 30 degrees, which is 5 feet, like this. So then so if we want to go RC with respect to A, again, A is over here, we need to go 8.66 in the I direction. But now we're not going to B, we're going to C. So we're not going to go up 5 feet. Remember, C is 2 feet below B. So if we're going up to C here, then this distance right here is going to be 5 minus 2. So then our RCA is 8.66 I plus 3J, because we're going to be using that in a minute here. So let's look at our equations to figure out what we're going to need. We're going to need omega cross RBA. So let's take a look at that. And omega cross. Now, the only thing is, instead of B, in this case, we're calling the point we're interested in C. So every place where we have B, we're going to replace it with C. So we're going to have our omega cross RC with respect to A. I, J, K. And remember, our omega was 2K. and our RCA was 8.66 and 3. And when we do the cross product, we get negative 6i, 7.32j. You can go ahead and take the time to verify that when you get a chance. Now we can put everything into our equation. Once again, we're going to replace B with C. And I almost did it right there. So remember C, replace B with C. And put in all our values. So remember, the main system, the moving reference, is not moving linearly at all. So that was our VA was 0 and our AA was 0. So that's going to be 0. We just calculated this up above. And our VCA was negative 1i. And so our VC is negative 7i plus 17.32j, like that. So that's our velocity of C. Now let's look at our acceleration equation. This equation here, of course, we said that acceleration of A was 0. That's acceleration of the main body. And then now we're going to need this value here, but omega dot is 0. So that's going to be 0. The cross product is going to be 0. So we don't even need to calculate it this time, because you remember there's no angular acceleration of the main body. Then we're also going to need omega cross RBA. So that, remember, again, in our case, that's going to be RCA. Now we've already calculated omega cross RCA. So we just have to cross that again. So we're going to have to do omega cross RCA. That's going to be IJK, like this. And again, our omega was 2K, and omega cross RCA was negative 6, 1732. And again, you can verify this on your own, but I calculated this to be 3464I minus 12J. So I ended up with this. Then we're going to also need this value here, omega cross RVBA. Now, in this case, it's going to be a RCA. And we get all that stuff from our front page. That was 2K. and VCA was negative I. And when you calculate those, you end up with negative 2J. And so let's just plug everything into our equation. Let me write the equation down so we have in front of us a C, a plus omega dot R CA plus omega cross R CA plus, and I should probably write it down here to have some room, plus 2 omega CA XYZ plus ACA XYZ. Now just plug in all of our stuff. Remember, acceleration of A, that was just 0. And this value here, remember, this was 0. So that's going to make this whole term 0, because that was 0. So that's going to be 0. And then this term here, we just calculated this up here. Negative 34.64I minus 12J. And then we need this term here, which we just calculated here, except that's multiplied by 2. And that was negative 2J. And so again, just to keep track of what we have here, remember, in this term right here, that was this one. This term was that one. And then finally, we have this ACA, and that was from our, again, from our first page, 0.5J. And acceleration of C is negative 34.64I. And if we put these together, this together, negative 15.5J, like that.